Thank you, Shweta. Good morning, everyone. So it's my pleasure to introduce Pascal Weil as our next speaker. Just a quick, brief bio. Pascal studied in France and the US. He joined CNRS in 1987 and has worked in CNRS labs since in Paris, Bordeaux, Chennai, and now again in Paris. He worked on automata theory, and more specifically on the connections between automata, logic, and algebra, as you can see in the title of the talk. He has recently been interested in automata for models of distributed computation, also in the title of the talk, and in algorithmic problems which arise in the theory of infinite groups. Pascal, as many of you may know, is a regular visitor to India and especially to Chennai. Since 2007, he has been the deputy director of RELAX, an Indo-French lab joint between CNRS, CMI, and IMSC, and largely they relax. It's my pleasure to introduce Pascal, especially since he was also recently our first speaker of the year at the Chennai Combinatorics Colloquium. So it's my second time this year introducing him. And over to you, Pascal.
Thank you very much. I don't think I need this. Yep. Thank you very much for the introduction. Thank you for the invitation. I'm very honored to participate in this inauguration, this first meeting of this new center. I think it's a great idea to have such centers anywhere, but notably here in India, in Chennai. So, yeah, it's my pleasure. Thank you very much, Shweta, for the invitation, and everyone else for the organization. As Nishad mentioned, I have many affiliations. The French affiliations usually are difficult to read, and when you have two, it's even more difficult. So this LIPN is a Paris North informatics lab. So you just shuffle the letters and you'll get it right. And it's a lab under CNRS and Paris North University. But I'm also, as Nishad mentioned, and together with Madhav and Mukund here, running a CNRS, CMI, Math Science joint lab, Indo-French, called RELAX. And RELAX is not at all what you think it is. It means Research Lab in Computer Science. The CS becomes an X, so it's very serious. And also it includes mathematics these days, so it's even more ambitious than just RELAX. Good. Thank you again. So let me. Oh yes, there's a clock here. Very good. Let me get started. Automata, logic, algebra, and models of distributed systems. As Nishad mentioned, these have been things that I've been working on over the, unfortunately, too many years. And so let me start from the start. So I'm going to talk about automata, logic, and algebra, how they relate to one another in the framework of languages of finite words, so something extremely familiar to most people who've taken a theory of computation course, and then, so classical results, and then I'll move to distributed settings, and there's many things that can be said in that direction, but I will be concentrating on results obtained fairly recently together with Bharat Atsul and two of his students, Shantanu Kulkarni and Saptarshi Sharkar, at IIT Bombay, and Paul Gastin and myself. Good. So, finite state automata, everybody knew at least what they are. Here's an example. So these are little pictures. Now, sometimes they say it's a 5-tuple, but it's not at all. It's a little picture. It's a graph with decorations. And here's another example. So what they do is you say, well, okay, what are the words here? The alphabet is 0, 1. What are the words that take you from, say, from state 1 to state 2? Oh, I think I have a yes. Ooh, yeah. State 1 to state 2. It's okay. So you see that this accepts. This first example, starting in 1 and ending in 2, accepts exactly the words that have at least one in them. And the second example, if you take state 1 to be initial and terminal, what does it do? Well, it excludes going to 3. and you go to 3 when you have 2 consecutive ones. Okay, so words that do not have 2 consecutive ones. So if you were into enumeration systems, you'd say, oh, these are the representations of numbers in the Fibonacci basis. Okay, so regular languages. Good. Now you can also describe words, characterize words, describe languages, using formulas, logical formulas. So you use predicates, A, one for each, for each letter A there's a special predicate, I wrote it in boldface, and binary predicates less than, and the variables are interpreted as positions in the word. So if you have a formula like this, what does it say? It says there is a position I, such that for every position j, position I carries letter A, and it is not the case that I is less than j. So, unless I'm mistaken, this means that I must be the last position. Okay, so it characterizes exactly that language. Capital A for me is the, I'm French, I'm not American, so alphabet starts with an A. It's called A, not sigma. I don't know why it's called sigma elsewhere, but I'll stick to A. Language A star A, all the words that end with A, is characterized by this small formula. And there's a theorem, very old theorem, Buchy 1960, that says that the language is regular if and only if it is defined by a monadic second order formula. It's MSO definable. What does monadic second order mean? We don't need to get into the details, but it means that you write formulas like this with these predicates that I mentioned. You're allowed first order quantification, as I used here in the example, but you're also allowed to quantify over sets of variables. So you can say there exists a set of variable capital X, such that blah, 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 and then you can say, well, this individual variable is in X or is not in X. Good. So that's a logical characterization. It's completely equivalent. It's intellectually very nice. It's not necessarily super practical in terms of either readability, because these formulas are difficult to read, or algorithmically. So you're not going to write your specifications in MSO, probably not. And there's an algebraic characterization, which is something quite natural, I think. You have your automaton, has a state set, Q, that's a finite set, and each word W defines a map from Q to Q. I'm assuming that my automaton is complete, so you read your word W from any given state, you reach some other state. That's a map from Q to Q. And maps from Q to Q can be composed, so they form a monoid, which I wrote Q to the power Q, all maps from Q to Q. And so now, from my automaton, I now have a map that associates with each word a map from Q to Q, and it's compositional, it's a morphism. Okay? And what is the language as accepted by my automaton? It's exactly those words whose transition from Q to Q takes the initial state to some final state. So it's the inverse image of P, where P is the set of maps, Q to Q, that take the initial state to a final state. And you make that an abstract definition. You take any morphism from A star into a finite monoid, into any monoid you want, if you want. And you say that L is accepted by that morphism psi if there exists a subset P of the monoid such that your language L is inverse image of P. Okay, and with what I give you, you have all the elements to figure out that a language is regular if and only if it's accepted by a morphism into a finite monoid. Good. So these are the sort of triangle of interactions. Automata, which is sort of combinatorial or maybe sort of algorithmic, I don't know. Algebra and logic that all match perfectly in the case of finite words. And so when you start your career, as I did, into this magical world where everything matches, then you're very unhappy when you step out of finite words and discover that things don't match in more generally. And why is it interesting? Actually, you have this matching between these three different things, and Um, so you can refine, you can ask now, you have more tools to talk about your languages. If you have only automata, what are you going to do? You're going to say, oh, I don't know, I mean, it has 7 states, or it has an even number of states. I mean, there's not much you can say about the automaton. Regular expressions, you can, which I didn't mention, but is also a classical companion to all these, you can say some things, like there is no second order quantification, for instance. So it's first. No, sorry. There is no star used in the expression. So it's what's called star free. But much more than that, it's not so convenient. But algebra gives you a lot of things, and logic also. So, for instance, you could ask, well, okay, so I said, Buchy says use MSO to describe all regular languages. Why not stick with FO, first order? Is that sufficient? Maybe it is. Okay, and another question. No, so, okay, not another question yet. The answer, no, it is not sufficient. But how do you prove this? How do you prove that there is no first order? How do you prove that the non-existence of something? You need a little bit of structure behind. Otherwise, it's not going to work. And a companion question is, well, I give you some regular language. Is it first order definable? Some are. My answer no says some aren't. How do you know? How do you find out? And there's a theorem, 2 theorems actually, but combined, this is the statement from the 60s or late 60s. And let's say L is, a language L, is first order definable if and only if it is star free. That's what I mentioned earlier about regular expressions. Something that's nice to write, but doesn't tell you how to decide. And if and only if it is accepted by an aperiodic monoid. What is an aperiodic monoid? It's one in which, for some n, an n being you can take to be the cardinality of the monoid, so it's something you can check algorithmically, satisfies x to the n plus 1 equals to the x to the n. Okay, so this last property is decidable, and that makes the other 2 decidable, which was really not obvious. And as far as I know, there is no other proof of the decidability of first order definability or star freeness than this one that goes through the monoid characterization. Of course, you can massage a monoid characterization into something about automata, because you go, I'm not going to get into the details here, but you go to the syntactic monoid of a minimal automaton of your language that you can do algorithmically. And the syntactic monoid is, it's enough to see that the transition monoid of that guy is aperiodic. And so you can retranslate algebraic properties into the minimal automaton, but fundamentally it's because you have something algebraic behind. And there's many more refinements that you can take. Some of these words may be familiar to you, like piecewise testable languages, locally testable languages. I'm not going to get into the details. Sigma 1, which would be some refinement of first order, or FO2 definability. FO2 means you take first order formulas, but you allow yourself the usage only of 2 variable names, which you can reuse through scopes of quantification, but you allow yourself only 2. If you allow 3, you can do anything that FO can do. But 2 you cannot. And what do you get? Well, something smaller. And there's a super interesting class. But we're not going to get there today. But the fact is that all these classes, membership in all these classes is definable, and is definable through the algebraic characterization. So this is where we are, I think. Yes, one more thing. That's almost the end of my advertisement page on algebra. And another result, which will play a role later in the talk, is this. So let me define first what's the cascade product of 2 automata. So you have 2 automata, A and B, and you run an input word W into the first, A, and you output the computation of A on input W. So what do I mean by that? You output you output a copy of your word W, but now you've decorated every letter with the state of A that you were in reading it. Okay, so that's what I call the computation of A. It says, on input W, letter after letter, I've been in this state and that state of A. And now you take that word, which I wrote chi A of W, to be an input for a second automaton B. Okay, so it's like what do you call that? A series composition of automata, a cascade. It would be better if it was vertical for the cascade. And right, so that's an operational automata, produces a new automaton, more complicated. This can be translated in algebraic terms. It's called a Ritz product of monoids, but it doesn't matter. The thing is that there are some basic, simple automata that you can use, and Krohn and Rhodes in 1962 proved that every regular language is accepted by a cascade product, not of just two, but a lengthy cascade product, of group automata and reset automata. What's a group automaton? A group automaton is one in which every letter is a permutation of all of the state set. So, yeah, injective or deterministic and codeterministic. And a reset is something like this. In a reset automaton, there are three kinds of letters. Letters like C that do nothing. Letters that like A that take wherever you are, they take you to state 1, and letters B, wherever you are, they take you to state 2. That's the reset automaton. Okay, and Krohn and Rhodes said, incidentally, there was their PhD thesis, and it was at MIT, and it was not very long, I think less than 100 pages, and it was their joint PhD thesis. I don't know that it has happened before or after a single piece of work be two PhD theses. Anyway, at the time it was considered quite a breakthrough, and right, so they say anything you can do with an automaton you can actually do by this cascade composition of very simple automata. Good. So now let's go to distributed models. As I hinted before, a lot of the things I mentioned collapse or are not yet elucidated. Like what's the proper algebraic framework, for instance, for distributed models. Anyway, there's lots of different distributed models. So what I mean here is that we have a distributed system, so there's a set of individual processes, okay, and each of them is their own little finite state machine. Each of them has their own alphabet of actions and finite state behavior, okay, and they communicate. And there's many ways in which this could be defined. I will concentrate on one single way, which is called Mazurkiewicz traces. I'll try to explain how that works. So, in fact, the way it works is that some letters are shared between different processes. So if they happen, if those letters happen, then they happen on the different processors that they belong to at the same time. So they synchronize, these actions synchronize these different processes. Okay? So formally, my alphabet A is equipped with a location map that says, okay, so my letter A, every little letter A, has a set of locations, a set of processes. Okay? And the combination of this location map and the set A is what I call the distributed alphabet. And you understand that if two letters, two actions, do not require the same resource, do not act on the same resources, or have disjoint locations, then they're called independent. There's no way that they know that that the other one is happening or not. So they can commute in some sense. They're not ordered neither causally nor temporally. And the trace monoid is the quotient of the free monoid by the relation that says, okay, so independent letters commute. Okay, So that means that there's a natural way of taking a word on A and leading to its trace, which is its equivalence class for this thing. And conversely, but I'll get back to what traces really look like. And conversely, if you take a trace, you can take its inverse image. It's the set of all the linearizations of that trace. So here's, I think, the right way, or a right way of looking at traces. So in this example, we have 4 processes. So the set P of processes is 1, 2, 3, 4. Okay, and you can see each letter. So the letters that we have, A1, A2, A3, A4, B, C, D, E, you can see on the picture what their location map is, right? A1, A2, A1 is located only on process 1. B is located on process 3 and 4. E is located on process 1 and 4. Okay? And right. And so now you have this word. Maybe the word is A1, A1, B, C, D, A3, E, A2, B, C, A4. I'm sort of going left to right on my picture. Why not? That's a word. But now I can commute some of the things, some of the letters, if they are independent. For instance, this B has no connection with C or with A1, so it could have been pushed there, but not further, because it will bump into the D that is also on process 3. On process, 3. And the E that is here could, or this A2 if you want, could move here and no further, but the B could not move to the left of the E. Okay? So when you take a word, if you think about it, and maybe it's like also playing like Tetris, it's like a horizontal Tetris. You put I don't know who remembers what Tetris games looks like, but you know, you put your letters as they come in your word and push them as far left as you can, and you'll get this picture. And then you can also shift them around. Okay, so a trace for me is a poset like this, where every processor 1, 2, 3, 4 corresponds to a linear order, but the whole thing is not a linear order. Okay. Very good. And right, so you can even ask things, you know, like, okay, so when I'm here, this process E9, this event E9, this is a B there. I'm on process 3 and 4. What do I know that happens on process 2? Well, I am not aware of this A2. What else is on process 2? This D, event 5. Am I aware of it? Well, yes, because as being here on process 3, I'm aware that there was an A3 before me, which is aware that there was a D before it. Okay? So I have no information about the A2 or the C up there, but I do know certain things. Okay? So there's this causality, this poset that I'm describing. Okay. Now, a trace language is said to be regular if the set of its linearizations, all the words that lead to these traces, is regular. Is there a, so now that definition, the word regular is out there, is there an automaton model? Yes, there is. Zelonka introduced asynchronous automata that implement this distributed structure on the distributed alphabet. So what do these automata look like? Very difficult to draw, so I did not attempt. But as I mentioned at the beginning, each process has its own finite state control. So for each process I, there is a set of states, Qi, and the global states are the tuples of states for all the processes. Okay, and when I look, so just a bit of vocabulary here. When I look at a single letter here, and here I failed and I put a sigma instead of a capital A. some contamination is there. When you look at a single letter A, let me call QA the tuples of states of the processes that intervene in letter A, or that A is located at. Okay, so not all states are in log of A, but this restricted tuples, not global states, but just restricted. This is what I call an A state. Okay, and now in a Zielonka, in an asynchronous automaton, each letter A acts. It acts on the global states, on the tuple of all states, but its action depends only on the A states it sees, and it will transform only those. So the action of A, the transition delta A, will turn Q sub A, these tuples of states in location that belong to A, into another tuple. Okay, and it will leave all the other components of the global states for processes I that do not belong to log A. It will leave them unchanged. Okay. So this really tries to take into consideration this notion of this distributed computation. What A sees as an action is only the location of A, these processes that are in its log A, and it is not aware, so it does not depend on, and has no action on the other processes. Okay, and then you choose a global initial state, global accepting states, and Zielonka proved in 1987 that a trace language is regular if and only if it is accepted by such an automaton. And it's a very difficult, very technical theorem that has led to a lot of literature in the ensuing years, with people trying to understand what was behind this this construction, how to understand the interaction between the distributed structure and the automaton, and in particular Madhavan and Mihin Sohoni had a very interesting work that also was followed by a lot of literature on so-called gossip automaton. Yes?
Is there a simple notion of a synchronous automaton?
So the synchronous would dilute or forget in fact about the distributed structure. It would say, okay, so I am forcing my B here to be before the C, or the contrary, or the opposite. So it would forget the asynchronicity means nothing more than the fact that I don't choose a representation. I choose the poset representation, not the linearization. So I don't choose whether B is before C or not. And so if you take this definition and you say, okay, so I have a trace language which is regular. So behind it there is this the language of words of linearizations, which is regular. There's an automaton for this. This automaton has some particular properties that you can fix, that you can check. You know, if A and B are independent, two letters are independent, that means that they commute. So in your automaton, at least in the minimal automaton, if you can go from this state to that state by A and then B to another state, you can do, maybe by a different route, but from the same place to the same place, using BA. So this is called a diamond property, diamond automaton. That would be maybe the synchronous version of those. But it could be that AB is equal to BA, or labeled as passed from the same place to the same place for other reasons than independence. Just because in that particular language, those letters have the same context, the same syntactic context. And so you lose something by going synchronous. The asynchronous is the way to account for the distributed structure of the distributed structure, and hopefully to account for the properties of the system we are modeling. Does this answer the question?
I asked because of the distributed algorithms.
We take synchronous and asynchronous. Of course, asynchronous is completely events-based, right? And synchronous gives you a time step, right? Kind of
Right.
thing. And that allows us to, say, make a lot simpler algorithms, or certain things you can do in synchronous far more easily than you can do in asynchronous, in that way.
Right. So, in some sense, it's the same situation. You know, it depends what you want to do with your language. If you want to say is it regular or not, you don't need this Zelonka distributed asynchronous automata. The automata that I described on this language of linearizations is enough. But if you want to, if you want to go in the direction of finer questions, is it first order definable? Is it this? Is it that? Maybe it's going to help. Maybe you're not going to be blocked because you are forgetting about the distributed system. You've fixed, you've rigidified your a priori nonlinear order. And if you're going to implement it, like you have a specification from some logic, and you know the distributed structure of your system, it is what it is. The processes are what they are, and you want an implementation on that distributed system, you cannot ignore that structure, at least in an abstract way. So this is really the question of what you need to use to solve a particular algorithmic, for instance, or implementation problem. That depends on the problem, and we're sort of like one step back from that question, trying to remain true to the distributed architecture. Is there a logical characterization? So yes, but it's a little disappointing. So I think you also have monadic second order logic characterization, and with the sort of the analogous result proved by Wolfgang Thomas in the late 80s. And there is a maybe more interesting, exciting at the time, 1992 result that says, and first order definable is also equivalent to star free. So that's good. That's good. But so then you would say, okay, so now tell me something more about, I don't know, sigma 1 or b sigma 2 or some other refinements of the first order hierarchy, for instance. Or tell me about algebra. Is there an interesting algebraic structure to represent, to account for these trace languages? So in some sense, yes, going synchronous. You have your regular language of linearizations, and it has a monoid, it has a syntactic monoid, and you can certainly characterize the fact, this is in the definition of a regular language being a trace language being regular, by the fact that it's the syntactic monoid of all the linearizations is finite, because this is almost a definition. But it doesn't. It works for first order. It tells you, okay, so there is a decidable algebra-based characterization of first order. But when you go to smaller or different subclasses, nothing very interesting has happened, or extremely complicated. There were some results by Kufleit that were very complicated and sort of super topical. I mean, there was like an ad hoc sort of solution. So the algebra part is still, in my view, missing. And also, there is no simple and meaningful way to go from an MSO formula to an asynchronous automaton. That means to an implementation. And so there comes into the picture some other logic, not MSO, but propositional dynamic logic. That's something that started in the late 70s by Fisher and Ladner's introducing this framework to reason about programs. And then there was an interpretation of the words, which turned out to be equivalent to regularity, to MSO. And then with my co-authors, we introduced, maybe Paul Gastin had introduced it before, local propositional dynamic logic. I'll explain why local, but meant for traces. So, if you've seen propositional dynamic logic before, then you know that there are several sorts of formulas, and there are so-called event formulas and path formulas. So here are the what is it called, the syntax, the semantic, whatever, that thing that says how you build those formulas. So the event formulas, as their name indicate, are going to be evaluated at specific events, so points, positions in my trace. And either they say, well, this is letter A, or this is Boolean combination, or I can do a path formula from my position, and at the end of that path formula, some pre-existing formula phi will hold. And then the path formulas they will be evaluated at a pair of events. I'll say there's a path from this event to that event, and in my trace. And the path can be just staying put and testing whether a certain phi event formula is true. Or it can be, let me go backwards. Let me first assume that I am an I event, I'm on process I, and let me go backwards some amount of time on that process I, so that's why it's called local. And then check whether phi holds. Or let me go forward, or let me take disjunction, concatenation, and star of such properties. So there's some kind of regular language of paths that's going on here. Now, how do you interpret that on a trace? I could put a very long and very boring and unreadable slide, but I borrowed a slide from Paul, which has lots of colors. I don't know how to do this myself. And so here is a trace. Okay, all the dots are events, or extended dots, events that are on several different locations, different processes. And the little phi's, phi 1, 2, 3, 4, 5, 6, are properties that may or may not hold at a given event. Okay, and I'm looking at this formula, this event formula, phi, and you can see that phi is, there's these angle brackets from here to there, and then phi 6. So, and then in between, in here, I have a path formula. Okay, the path. So, how do I interpret this? I am saying that this phi holds here, of this black dot, black event, if there is a path, if I can follow a path that satisfies, that's described here, to a place where phi 6 holds. Okay? And what does my path say? It says, first you go along process 3 to the right, making sure that phi 1 holds all the time. Okay, so that assumes that I'm already on process 3. This is the case in my black dot. I go forward, making sure that phi 1 holds all the time. And at some point, I test for phi 2. Okay, so maybe phi 1 holds here and here and here. I don't care. At some point, I decide to stop. So it's non-deterministic in its definition here. And I test for phi 2. And phi 2 happens to be on process 2 and 3. And now I go further to the right, but on process 2, I'm allowed to do that because I've reached this guy, making sure that phi 3 always holds, and at some point I stop and test phi 4. And I'm here. And then, because phi 4 is both a, how this event rather is both 1 and 2 event, I can certainly do this, go backwards on process 1, making sure 5 holes. And then I reach a place where 5 6 holes, this 5 6 here, so I'm happy. Okay. So this is how you, I think with that example you can like figure out any, the semantic of any event formula. And good. So, right. So this is local PDL. And then there's a restriction if I don't use the forward thing. It's called local past PDL for obvious reasons. Okay. So why is it interesting for traces? It's because it really builds in the notion that you are looking at process I events at some given point. Your movements along the trace are totally event. They're local to a particular event, to a particular process. Okay, and a theorem that we proved took us a lot of time. It was several different papers. It's rather quite technical. Is that this local pass PDL is expressively complete for regular trace languages, which means precisely that the language is regular, trace language is regular, if and only if it can be defined by a local pass PDL formula. Okay, so this is good, but a little gratuitous at this point. So what we're trying to do then is like use these formulas to actually synthesize, so out of the specification given in local pass PDL logic, synthesize a synchronous automaton in a way that's structured. So the way we did this was again using this notion of cascade product, but this time of asynchronous automaton. So it's exactly the same idea. You have an asynchronous automaton A, you feed it a trace T, you output the computation of T by A, which means that you've decorated your trace A with the state. Now the states are rather complicated, right? The global state, they're tuples, but it doesn't matter. You've decorated your trace T by the states you're in, and then you fed that as input to another automaton. Okay, and you started with a distributed, your trace is over a distributed alphabet A, or a tilde with the location. So now the output here is labeled by pairs of a letter and a state, and you need to say what is the distribution, but you just take the distribution on the first component. Okay, and again you're going to use basic bricks, and the basic bricks are the same as for words, permutation automata and two-stage reset automata, but I want to see them as asynchronous automata over my given distribution, which I don't choose. So I'm going to take localized versions, which means they happen only on one particular process, on process I. The two states are on process I, and on every other process there's a single state, and every letter is the identity. So nothing happens of any meaning or significance on the other states, on the other processes. So localized group automata, localized two-state. And with the same authors, or a subset of the same authors, we proved this statement, so that any regular trace language can be realized by a cascade of asynchronous automata. And they're missing a bit of it, in fact, of these particular localized group automata and localized two-state reset.
So is the converse true? If anything can be realized as a
Yeah,
cascade?
because if you compose cascade automata, you get another automata, and so something that's regular. That is the easier part of the theorem. Okay, so right. How much time do I have? Difficult question. Oof, too much. So let me give you an idea of how this works and how it connects to my logical apparatus and why it's interesting. And the last part, I don't know, you're going to be the judge of why whether it's interesting. But so the statement I gave is to say every regular trace language can be accepted by a cascade of basic localized simple automata. But really the proof is out of a locally passed PDL formula, I will manufacture my cascade product. So I'm going to use the natural structure of a formula, the recursive structure of a formula, to construct, to prove my theorem, but also to have my cascade product appear in front of me. So the key point in this proof is to compute for each event formula an asynchronous automaton, which, preferably one that is a cascade product of basic localized automata, an asynchronous automaton which on input a trace t will output the same trace decorated by the truth value of phi. You know, at this, see my trace that I push in is a bunch of events, and at each event I want to see which letter is there on the trace and whether phi holds or not in that at that event. So you want to do this by structural induction, so you start by the simplest formulas. If phi is just a letter, well, that's very easy. The letter is on a given process, and you can manage that. Boolean combinations are not a problem as usual. And I'm not going to do all the cases. It gets terribly technical and somewhat difficult for some of them. But I'll give you a simple enough case here where your formula phi is of the form: go back on process I for a bit and verify whether that psi holds. And we assume that by induction we have already an asynchronous automaton that computes the truth values for psi. And is in the required form, meaning a cascade product of the small localized automata. And now let B be this guy. So I'm going to do a cascade of my A psi, which comes from previous induction steps, followed by this guy. This guy, first, before I explain the different decorations, it's a reset automata. It's a two-stage reset. Okay, a particular case where there's all letters either keep you in one place, or they take you to state 2. And what are my inputs? A trace, yes, but a trace on which distributed alphabet? On the alphabet that says, on the alphabet that has a letter and a truth value, true or false. Okay? And what does this say? It says, as long as I read any letter with false, I output false. At some point, in fact, the first time, whatever, but it's distributed, so there's no first time. But when I read a truth value, so when I read any letter with a truth value true, I change state and I still output false. And then I output true whatever I read. Okay? So if I combine my two things, I'm pushing my trace T through A psi, and it comes out a trace that's decorated by true and false, the same trace but with trues and false. And here I'm saying that when I'm pushing it, then on its localized at process I will output false as long as I see false for psi, and when psi becomes true, I'll still output false once, and then I'll output true. So that means that I've been going now I'm seeing that I'm going maybe next plus and not previous, but you would do the right left reverse. Okay, so it's like saying, okay, so I'm going forward with false, 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 and then as soon as I see true, I change state. So I'm going at least one step to the right, and then I'm staying there true. So that corresponds to the semantics of this, actually not prev I, but next I plus. Okay, and so the rest of the proof is of that nature, only it gets quite complicated for this case, with the case where you are saying, oh, and by event I can actually follow a path that itself has a complicated structure. And that part actually uses the classical chronoids, so the words, finite monoid chronoids. And okay, that's the proof, not the proof, but an idea about the proof of this result, that every local pass PDL formula yields a cascade product of simple localized asynchronous automata. So what we've been doing as a conclusion is talking about trace languages, which maybe not everyone was familiar with here, but that's a very standard model for distributed computation. And we've been revisiting Zielonka's equivalence between regularity and asynchronous automata. And this revisiting has been done through the lens of this particular logic, which has been proved to be expressively complete. The proof that it was expressively complete did not use Zielonka automata, it used the definition of regularity. And then this expressively complete logic I've used to prove a Chronodes type theorem, so cascade decomposition for trace languages, for regular trace languages, in terms of cascade products of simple localized asynchronous automata. So it's actually interesting that this distributed system can be seen as a cascade of localized, single process localized simple automata, but of course it's not always the same local, so the whole distributed structure still holds. And this provides a new, I think, more structured proof of Zielonka's theorem, because one byproduct is that indeed every regular trace language is accepted by some Zielonka automaton, but we even give more information, particularly one that's a cascade product, etc. And that's it.
Pardon my total ignorance on these things. Are there any connections to temporal logic also on these kind of things?
Yes. Yes. So, Madhavan will correct me if I say stupid things, but temporal logic, so in words it's like linear temporal logic, but now it's not so linear anymore. Can be expressed in terms of this propositional dynamic logic. And it has been studied quite a bit in the context of traces. So you have to modify a little bit the basics of temporal logic, but it's a rather natural thing. But temporal logic captures only first order definability. So it doesn't capture all of regularity. So that's an issue. Depends what you're trying to model. If it's first order, then LTL or temporal logic is good enough. And if the question extends to, but what about the cascade decomposition for first order definable. If we were in words, we'd say, oh, but you know, Cronrode tells us that if your language is first order definable, I mean Cronrode plus Schützenberger and the rest, if your language is first order definable, then you don't need to use this group automata at all. It's just a cascade product of two-stage resets. It's very tempting to think that the same thing holds for traces, but it doesn't. It doesn't. I mean, there's like a little bit of counting mod something that needs to be done, and but exactly what the final, from the book statement will be is not quite obtained yet. Working on it. So it was a very good question, in fact.
Any other questions? Okay. If not, let's thank Pascal again.